So very good morning and welcome back to the second session of day one for ATAL Academy sponsored 1 week online faculty development program on the geotechnical earthquake engineering. So we have with us Dr. Nilima Satyam ma'am for the second session. She is associate professor and head at IIT Indore. She is a doctorate from IIT Delhi, postgraduate in geotechnical engineering from IIT Delhi, and graduate in civil engineering from Sri Venkateswara University, Tirupati. She has received GSPS fellowship in geotechnical engineering laboratory at University of Tokyo, Japan. Her research field includes geotechnical earthquake engineering, dynamic soil structure interaction analysis, foundation engineering, liquefaction modeling, landslide hazard assessment and monitoring, rock mechanics, and underground structures. She is a winner of numerous awards like the Award for Young Teachers from AICTE, Government of India 2012, Young Women Engineer Award from INWES, International Network of Women Engineers and Scientists 2012, Young Engineers Award 2011 in Civil Engineering discipline from the Institution of Engineers India, Kolkata, India, Young Scientist Research Award BRNS Department of Atomic Energy India in 2011, Fast Track Project for Young Scientists Department of Science and Technology Government of India 2009, Best Technical Paper Award IGC 2006 at IIT Madras Chennai for the innovations in field exploration and in situ testing in 2006. We are honored to have you with us, ma'am. Thankful that you could manage time from a busy schedule and enlighten us over the burning issues. I request Nilima Satyam, ma'am, to please take over the session, ma'am.
Yeah, thank you so much for your kind introduction. And first of all, congratulations to Civil Engineering Department of IPS Academy. For continuously organizing, technical events. I should congratulate Amit and his team for, active outreach activities at your university. So thank you so much, and I'll be sharing my slides now.
Please.
You can see, right? Can you see my slides?
Yes, ma'am.
Yes, ma'am.
Thank you so much. Yeah. So the topic, whatever they discussed or organized, that is earthquake engineering, or in specific geotechnical earthquake engineering, is something very very crucial. Why? Because earthquake is like unlike other disasters. It is a very short duration event, like within few, maximum a minute, everything happens. Like it can create such a big devastation with a very short time, right? And a kind of energy that it hit the superstructure or built-in environment is tremendous. So how do we design seismic resistance, or like I can say resilient infrastructure, which is something Government of India is working towards it very rigorously in building the resilience, in our infrastructure for several disasters. It can be landslides, floods, or whatever it is. So let's focus on part of building the resilient infrastructure. What we have to do is understanding the physics behind the earthquake process. That is actually the core seismological process. That is very clear, right? And when you have an earthquake, or maybe because of fault rupture just after the earthquake, or at least even for a particular given region, there is some idea like, okay, this is seismic prone of approximately this much intensity, or this is moderate, high, or whatever way, right? That is what our IS code says, 1893, right? Seismic macrozonation maps. So with that idea, what we are going to do, if I'm building a house in Delhi or designing something in Delhi, so whether it is a South Delhi or East Delhi, so will that really have an impact on the hazard? To start with, yes, because earthquake happens in the rock, right? And at the crustal part. Okay, so where you have a rock somewhere below few kilometers, sometimes this rock can be at the surface. But mostly earthquake doesn't happen in soil, it happens in the rock. So it is just a failure of the rock, right? And when there is a burst in the rock, which is some X kilometers from the surface, or from the existing ground level. So these waves do pass, right? They just spread in almost all directions, and when they're passing, then obviously you have a soil above bedrock, then you have a soil. So when they're passing through this soil, okay, which is like highly non-linear, and this cannot be predictable because under dynamic loads, earthquake, the behavior of soil is highly non-linear, and how to quantify its response is something which we have to be very clear. So my topic today is on that particular aspect. How do soil, alter the seismic waves which are generated from the bedrock, from the much below, okay, the ground surface, when these seismic waves are passing through the particulate material and how they are interacting. Okay, so we do have a very clear theoretical or approaches of wave propagation in soil media that is very clearly established. So how to evaluate if I'm a design engineer? So how do I quantify that part? So when this seismic wave is passing through the soil and coming to the surface, what is the,
Ma'am,
hello? Yeah,
ma'am, sorry to interrupt you. Actually, the slides are not changed, ma'am.
I didn't move it.
Okay, okay, no problem.
So I'm
Sorry,
just
ma'am.
still talking on the introduction part about my lecture. Okay,
Okay,
so
okay.
now is it moving? Can you go? I mean, can you see that slide? I changed it.
Yes,
Yes,
ma'am.
ma'am.
Yes,
Yes,
ma'am.
ma'am.
Yes,
Okay.
ma'am. It's now visible.
No,
Yes,
I'm
ma'am.
just
Yes,
giving
ma'am.
you the introduction part. So the another part is like, when this, whatever the characteristics of my wave, that is seismic wave at bedrock, and when it is passing through the soil, okay, it do alter, right? It is a material. When a wave is passing through from one material to another material, obviously the wave characteristics do change. So when it changes and it is reaching to the surface, that value we have to give as input to my superstructure when I'm designing for seismic design. So this is what we have to do. So the ground response analysis, I am going to find out how my ground, that is the top soil, is, the wave has been altered from bedrock to the surface. So that's what ground response analysis. Okay. So why do we need to study that? Because as I already discussed something, so I can go quickly. It is very important. Why? Even at the planning stage. So as I said, like, so the response of the soil, because the soil is highly heterogeneous. Even if I'll take the examples, very frequent examples from Delhi, because Delhi has a very typical geological structure. If you take the entire city, NCR, South Delhi is having outcrop, that is rock is at the surface, okay, which we call geologically outcrop. Whereas if you go to Western Delhi, you have a thick soils, but they are consolidated soils. If you go to eastern part, Noida and other areas, they are like, very loose sediments are there, and of course they are also thick. So the hazard is not same because the material is different, right? I have a bedrock in South Delhi, I have highly consolidated soils which are having higher shear strength, okay, or higher shear wave velocity, I can say, in terms of dynamic soil properties in the Western Delhi. And in the Eastern Delhi, I have very loose data where shear wave velocities are very less. So obviously, when I'm building a facility of maybe same kind of structure, I'm doing some betting for this residential building in Noida recently for Godrej people. So they are putting something on shallow foundation, which we felt like it is not sufficient enough, because the problems of liquefaction and something comes in the Eastern Delhi where you don't find something such hazards in South Delhi. So hazard is like very site specific. Okay, so for to have a proper preparedness in terms of disaster preparedness, response or recovery, we need to have the detailed quantification of the ground response analysis. So the same thing which I explained you during my introduction, the same thing. So we do have a source. As I said, earthquake happens, that is at the source level, at the bedrock. So this is somewhere assuming few kilometers below the bedrock. So, and then when the wave is passing through the material, and you have soil like it's which is a layered strata. So during its path, okay, so it do had alterations, that is they do get altered. And when it going to the local soil, this is what we call as local soils. I mean to say, at least up to of course this is a debate, 30 meters or 45 meters, so people consider that as a local soils. So because after that overburden will take care of it. So this local soils, how do the wave get altered? So I have a source characteristics, I have path characteristics, and I have site characteristics. So I have to quantify each and every one when the wave is passing through three different materials. So which we are going to discuss. Structures, or like whatever you call it as built environment, any kind of thing. So let's consider something. So I have some below, assuming that 30 kilometer below the ground surface, this is the ground surface, I have some earthquake or some fault rupture happened, and then because of that fault rupture one second. Because of that fault rupture, seismic wave do generated, and then that waves got passed through, and then they reach the bedrock below the facility, that is below the structure, and then after that they are moving towards the soil, okay, and where they do have a lot of interaction. So if you see here, this is the ground response at the bedrock. See, whenever there is any earthquake, from the whatever the instrumentation or the seismographs, we can get this one, right, that whatever the ground motion, because most of the instruments are installed on bedrock. Okay, so okay, we get this acceleration or time history at the bedrock, and then we have to bring this to the surface. So for this to bring from this ground motion to this, what I need is like I need the complete dynamic properties of my substrate. Also says that even in seismic zone 3 and above, we should have to carry out the dynamic test, including MSW, that has become compulsory. Okay, so when you do such kind of thing, I'll get the complete characteristics of my strata. Okay, from up to at least like 30 meters, I need it. Even if the soil thickness is like 200 meters, as it is in some parts of Eastern Delhi, so I don't mind. But up to 30 meters is sufficient, because after 30 meters, my overburden 30 meters will take care of it. So what I have to do is like I have to bring this time history or ground motion to this surface, and this is an input for my design for my superstructure. Generally, people what they do is they do it as a fixed base. I don't know how do they can fix the base of any structure. Anyway, so this is something very important for a structural designer or a geotechnical designer for foundations, etc., to do this ground response analysis. Okay, as you know that our microzonation map has like 4 zones, 2, 3, 4, and 5 with the different levels of risk. So this is actually, if you see here, this is at a macro scale, okay, and which is considering mostly the seismotectonic and geological settings, but not considering the geotechnical characteristics. So this can be taken as only a base thing, but not actually as a Bible, so that you can go with it. Okay, because I have given the example of Delhi itself. Okay, so as I said, like when you have seismic source, when it is passing through, obviously the topographic effect, in the past case histories, when we seen that the especially during the Nepal earthquake, so especially what happened in the Kathmandu Valley, we had seen the more higher damage when compared to the portions which is on the hilltop, etc. So this is only because of the topographic effect. So it's the crustal part or the depression part, etc. So even that wave do had to change with the topography, which we are not considering, at least in this one, which we called as local site effects. If time permits, I'll cover this also today. So preliminary topographic effects, when we want to do this one, whatever is like homogeneous body, if you have a complete homogeneous soil, so obviously, whatever the ground response analysis, or, it may be easier thing, okay, in the sense like it will be in a kind of resonance frequency types, very simple equations we can use it if it is something like that. And another thing is, as I said, with the topography effect, we have another important factor which we have to consider is the geometrical factors. So which we have to incorporate when we do the ground response analysis. So before starting my actual talk, I would like to start with show you some of the past damages and how they can be quantified, or like in terms of damage intensity and also the pattern part of it. Let's see. As I said, like if I have a facility like this, again I'm taking the example of Delhi. If it is a South Delhi, we have a facility like this, and mostly on the outcrop, so you find rock. And whereas if it is in the Eastern Delhi or parts of Central Delhi also, you do have a thick alluvium, and the facility may be sitting like this on the soil. So when we have the similar earthquake ground motion, the damage intensity or the pattern will be exactly very different. You cannot compare it. Okay, and same kind of structure, same serviceability, and same type of foundation. That can be explained with this picture. This is a classic photo which is on the Kramer textbook. Most of you might have seen that textbook or read it. So if you see here, all these are residential buildings, some Niigata during the 1964 classic Niigata earthquake. And if you see here, all are like similar buildings, right? But after this Niigata earthquake, particular building has been completely collapsed. Okay, it was tilted. You can see kind of settlements here, and this is also tilted. Some of them fine, right? They performed very well. The distance is between this and this is only 8 meter and something around 14 meters or something. Even within few meters away, the damage is completely different, right? And so why is this? Because the soil is highly site specific. If you want to design for this particular, you have to understand how the behavior of the soil at that particular site. So this is a completely site specific study. Similar thing, another classic example is on Hansen Expressway, which happened during 1995 Kobe earthquake, wherein this expressway, only part of expressway was completely collapsed, which is almost like 630 meters. And people have done the analysis. Generally, after any disaster, we do like forensic analysis, right? So similarly, people have done that, and it was observed that there is an increase in the period from 0.65 to 0.9 seconds. Okay, wherein like the because of interaction of soil structure interaction effects, so it increased the period of vibration to 28%. So 28%, you can see the kind of damages that you can see. So 630 meters remaining portion of the Hansen Expressway was very intact. Only this particular portion of 630 meters has completely collapsed. Similarly, underground structures right now, even Government of India is having a lot of ambitious plans, for underground for underground tunnels, etc. How do these damages do happen? I'll just show you some of the photographs, so you can get something like a peripheral cracks after this, because during the Sikkim earthquake, so many Tista projects, okay, their underground caverns, especially the transformer cavern, okay, and powerhouse caverns had completely collapsed, and few of the caverns, some people were working, so men and machinery was also been, we lost them. So it was such a big disaster that happened in several Tista projects. You can see here the piling of the concrete. Okay, so longitudinal cracks too can develop. So this also happens, when you have the propagation effects. When you are the wave propagation is what is the direction of the wave propagation also matters. So all tunnels, especially even in the Tista projects, also there are a lot of Tista 2, Tista 3, Tista 4, etc., etc. The damage is not pattern wise or intensity wise was also not uniform. This depends upon highly on the topographical effect and also on the local site characteristics. So again, of course, the damage to the underground structures do depends on the rupture mechanism, whether it is having a reverse fault mechanism or strike slip fault, etc. Okay, the another hazard that we have to handle is the liquefaction part. I do had one interesting consultancy project. Okay, it was actually a flyover bridge. Okay, and they started sometime back in 2014, and then they designed it, everything. They started the construction as well, but there was a query of liquefaction because that was in seismic zone 4, and since it came out, they want to redo the analysis. Okay, so when they did the analysis again, yes, it was liquefaction prone. So again, mitigation measures have been considered. Then the project has been delayed for more than 4 years. Okay, because of this process. So liquefaction is one of the very interesting and complex phenomena that we do observe, especially during earthquakes. So what happens is the soil behaves or like a viscous fluid. Okay, and when it is like a viscous fluid, can we imagine standing on such kind of material right now? Right? No, right? So because it doesn't have any shear strength, so it loses shear strength for only some time, and then again it regains the shear strength. So during this process, your structure may fail completely. Okay, you don't mind like if it gain again after a couple of minutes, so how does it help you, right? It already liquefied. So these are the kind of you can see here there is no fine crack also on the superstructure, but it is collapsed, right? So these are the geotechnical hazards. Let me tell you, if a geotechnical hazard happens, your structure will completely fail. Okay, if a structural hazard comes, it doesn't matter like if it failed completely or not. Okay, it doesn't you cannot guarantee. So most importantly is the geotechnical hazard. So why do we underestimate? Because we could not understand the behavior of the material, that is the soil here. It's not my concrete or like my slab or whatever, column, or my foundation is taking the load. It is actually all these are transferring elements. Finally my soil is going to take the load. If it stop taking the load, obviously your superstructure should fail. So some of the port structures also, I think tomorrow my student will give you talk on port structures. So Swati, so I think I don't want to do that. Okay, the foundations, you can see the kind of failure that happened, for the, some of the classic examples. You can see this is again Kobe earthquake. So how the piles have been failed. See the response of the piles during this. This is again Kobe earthquake, okay, for a storage tank, and complete liquefaction and lateral spreading. When the soil around the pile has washed out, how do we transfer the load, right? So you can see here, this is between the connections. And these are the piles, how they damage. They are not columns. Okay, what happened to the soil, embedded soil? It has been washed out because of the lateral spreading. Retaining walls, you take any structure, and this is during the Uttarkashi earthquake in 1991. You can see the failures. Okay, so with this one, let's see how to quantify that with considering the path effects and also the site effects. So for that, you have to carry out the ground response analysis. First one is like to quantify the source effects, obviously rupture mechanism of the type of earthquake, how the earthquake happened, all these things that comes under rupture mechanism, the source mechanism. So that you have to have it. Mostly this is the easiest part. Okay, you can get it just after an earthquake or even before an earthquake. If generally people, seismologists, they do a lot of work on such kind of things. And then second one is like path effects. When a wave is passing through the material, because seismic waves pass for kilometers, right? When a Bhuj earthquake happened in Kutch region, it passed through up to Ahmedabad, right? Ahmedabad has severe damage when compared to the Bhuj region, which is near to the epicenter. So why do you think so? Because when a wave is passing through for longer distance, the energy should die, right? The laws of physics. But here the laws of physics doesn't apply, because the wave gain its energy when it's passing through the loose sediments. Okay, the Ahmedabad, which is almost 200 kilometers away from the epicenter, experience more damage when to the buildings which are near to the epicenter. Okay, so which is completely against the laws of physics. So that's where we have to be more focused. Why? Because when a wave is passing through the loose sediments, it amplify, which is called as soil amplification, and you have to evaluate that too. So and then the site effects, that is local site effects. How my local soils, that is my below my foundation, at a particular facility, the 30-40 meter soil, how they are and how do they behave during the seismic load is a matter of concern. So in reality, mechanism of this fault rupture, as I say, it's complicated, but it's not our cup of tea because it's mostly seismologist part. So, but we may need some parameters from them, like we need the crystal velocity, damping characteristics when we really want to do the remaining part of the ground response analysis. And another thing is like hazard. I'm not talking about the hazard evaluation because it's mostly clear. Most of the people do this even in the industry when they are doing seismic design. So it can be done through deterministic approach or probabilistic approach, depends upon the importance factor. If it is a kind of nuclear power plant, we do deterministic approach, but probabilistic approach can consider more uncertainties and can predict the actual behavior or hazard. So we can do, and then once you do this, like after the hazard analysis, we can develop our own attenuation relationship to predict the ground motion parameters. Once you have that, then you have to do the ground response analysis considering the detailed geotechnical parameters. This is like that. I have somewhere bedrock, okay, assuming some few kilometers, 100 kilometers, and I know the ground motion here. And when I have an outcrop ground motion, like rock is up to the surface, like the case of South Delhi. So mostly in rock, you behave like a mostly elastic. So there won't be much change in the ground motion. I can consider the bedrock motion as outcrop motion, maybe same. Okay, but how to bring this to this level is the thing which we are going to do now. So for ground response analysis, so we generally we are used basically to predict the surface motion, like what is the surface characteristics of my wave, okay, which I have to take, because that is the characteristics of the wave which is going to hit my superstructure facility. So to predict the ground surface motion, especially if you want to design something, develop something for the response spectra, etc., and also you want to evaluate the dynamic stresses and the strains for liquefaction sort of geotechnical hazards, which are common, especially when you are sitting on the soft soils, and to determine the earthquake induced forces which can lead to some kind of instability, especially for returning structures. So for ideal condition, this analysis, would model like source characteristics, path characteristics, and of course the site characteristics. So we have to have all the three things. I'll just skip this. So in reality, that is actually as per the physics part of it. But in reality, what happens is, like, the source character, as I already explained, the bedrock ground motion and the outcrop ground motions, we consider it uniform because of the elastic behavior of my rock. But rocks are not completely elastic. If they're highly disintegrated, highly fractured, weathered, they're not completely elastic. But intact rocks, mostly they will be elastic in behavior. Okay, so in practice, like, whether you do it like probabilistic or deterministic approach, so up to bedrock, you can get the characteristics of my, especially when I say the ground motion characteristics, generally we quantify that in terms of peak ground acceleration. So when I do either from my hazard analysis, either considering probabilistic way or deterministic way, I do get my PG at the bedrock, right? So after that, I have to carry out my ground response analysis, which many people, even industry, are ignoring. They think that after hazard estimation, whatever the ground acceleration that they got at bedrock, they are going to use it for the design. Then you are not considering the effect of the wave propagation, or in that soil on which your structure is sitting, right? So that is one of the biggest problem at present. So that's the reason why I consider this particular talk now. So ground response analysis is something very, very crucial, so that you can quantify the hazard in a more site specific way. So there are different ways of doing it as well. So first we have to predict ground motions like time history or response spectra. Then you have to evaluate the stresses and strains for liquefaction hazard, and of course to know the foundation loading. And then the failure, whatever the ground failure potentials for instability evaluation for its returning structures and its response. So these are the terms which we will be using. This is the bedrock motion, this is the outcrop motion, this is the ground motion or the surface motion. Okay, so this is the terms which I will be using from now. So mostly bedrock and the outcrop motions we consider same, and this is the important parameter for me to decide if it is sitting on the soil. Okay, so if you know that this is measured like from instrumented data, so that means like bedrock motion is known, or even from the hazard analysis. So since I'm assuming that this is material is elastic, this is also known because this is known same, and only unknown part is this. Okay, so in some cases what happens is like because NGRA and Ministry of Earth Sciences, they install a lot of instrumentation such seismograph stations at different parts of the country, and for quite long time they have a very strong network. Mostly the instrument, they prefer to keep it on the rock. So if you have very shallow depth, some rock is there, so what they do, they excavate, they put the station station types, and then they instrument that. If they could not find it, what they do, they put it on the surface. Okay, when they put it on the surface, it will give you the surface ground motions, right? And when you have the surface ground motions, and you can do back calculations so that you can get this particular part. So in that way, people also try to, because you have this thickness is like some 100 meters or 200 meters, you cannot do that excavation for such a deeper depth and put your instrument there. So for that, what we do is like we can have this at the surface station so that you can measure the surface ground acceleration, and since you know this, you go back. So this is possible also. based upon the type of location of the instrument that we do. Okay, so let me explain you how to do this ground response analysis or site response analysis. It has basically two steps. One is like the detailed modeling of my soil profile, because soil is layered and each layer has different dynamic soil properties. Its thickness is varies. So I'll consider the shear velocity as the dynamic or shear modulus, and then thickness of each layer. And for of other motions, actually we try to calculate at each layer. Okay, and then we try to calculate the final one response at the surface. So I'll be quickly explaining the methods and I'll take the example as well. So first one is like in the first step, that is a modeling of the soil parameters, since the soil is stratified. And as I said, like I need the dynamic soil properties, shear modulus and damping characteristics. So we can carry out, right? We can calculate this, like you do MSW test, you get shear velocity, and I can with density, if I have, I can calculate the G. So once I have this, of course the damping also I can. So I have the soil models for shear modulus and damping characteristics of each kind of soil also. And I know the thickness. Okay, so then we can carry out either one dimensional, two dimensional, or three dimensional, based upon the type of or importance of that particular facility. And then mostly people do one dimensional also, because most of the cases the changes, or I can say the difference is not that much, so people try to but for important structure, very very important structures, we tend to do even three-dimensional analysis as well. Then calculating the top of profile motions, like how do we do this? Typically, we have bedrock motion is being given. So I will be from bedrock to if I have a bedrock unknown location, some locations we don't know where is the bedrock exactly. So because we cannot drill boreholes to find out the bedrock or something. Even if you do some sort of refraction studies to find out the bedrock ground motion, we may not able to find out actual bedrock. Maybe engineering bedrock we can get it. Engineering bedrock is nothing but this there may be if you go there and do the excavation, you see that it may not be rock, actually it may be soil, but behaviorally it behaves like a rock. So when the material is highly consolidated and very very strong, so very compact, then it may behave like a rock. So as per NEHRP classification, if the shear velocity is more than 760 meters per second, we consider that material as behaving like a bedrock, which we call as engineering bedrock. Actually, it may not be rock at all. So, but it behave like a rock. So for us, it is our problem is solved. So location of this engineering bedrock, even if you don't have a bedrock, actual bedrock, depth, if you don't know, if you have that up to your engineering bedrock, if you have the detailed dynamic soil properties of all the layers, then what you have to do is you have to find out the response at each and every layer. Okay, so for doing that analysis, we can do linear analysis, quarter wavelength approximations, equivalent linear approach, or non-linear approach. So I'll be explaining equivalent linear analysis now, and of course these are the methods we do. Non-linear analysis, people try to do it when the facilities like nuclear power plants or very important facilities are there, where the risk level is higher. So I have a layer like this. Okay, so in different layers I have, and I do have the thickness, shear velocity, damping characteristics, and of course the density. I do have all the parameters for each and every layer. What we do is like the wave is coming from the bottom, right? And when the wave is coming, it do have reflection, refraction, all sort of things. So when wave is going, and because of this interface effects, okay, so there is a modification. I have this level. I have to find out what is the characteristics of my wave because of this interaction. Then again another level. So at each every layer, I do find out my ground motion characteristics. Okay. So whatever comes at the surface, I'll be taking that. So in the linear analysis, that Fourier amplification, okay, we can calculate. So this is actually for one of the sites, which is at the hard rock site. Okay, this is what I'll be explaining you. So equivalent linear analysis is very very common. Of course, most of people use the commercial software like Shake or ProShake, whatever. So what it exactly do is like it starts with knowing the G value and damping value. Okay, and linear response analysis for each layer it will calculate, and then it will also it will check the consistency with effective stresses. And if it is there, it's fine. It gives you the output like this, and it doesn't, again, it will go and do the same trials again. So this is like, comparison between the linear and equilinear. So from the literature, so how the Fourier amplification changes, you can see here up to the frequency of 1, there's not much difference. Okay, the difference was minor, but after that, between 1 and 10, the frequency range, so there is a huge difference. And the different material, like if a structure is sitting on a rock, or like, or maybe soft soils or whatever it is. So generally rock considered to be more of elastic, and there won't be much change with the ground response characteristics. But whereas if you see the same thing with linear and equilinear approaches, these are the something like, response spectra differences. As I said, like, this is how the hysteresis loop of the soil look like. If you, of course, it doesn't have the nectar thing, but anyway, so when you do the dynamic test on soils, okay, so this is actually the stress strain curve look like. What can you take it? Stress strain curve is such an important thing for us to understand the material characteristics. So what kind of inference we can make? That's why I said soil is highly nonlinear. If you want to take the nonlinear aspects of the soil, okay, so of course we do have like nonlinear inelastic characteristics, including the plasticity effects and pore pressure generation details. We can do any sort of nonlinear or dynamic test in the laboratory, resonant column or cyclic simple shear, etc. And we do have some programs. Of course, these are like a bit costly programs like FLAC or Dynaflow, etc. So let's see what is the change we do have from equivalent linear and the nonlinear analysis. So, but nonlinear analysis need, very robust constitutive model, which may require a lot of data. So which you have to do it from either laboratory, as I said, you have to do resonant column, or like, extensive field test can be carried out. Whereas, in equivalent linear, it do assumes like, some sort of nonlinear models, they are considered in terms of effective stress, so that it can model the generation of the excess pore water pressure. So whatever the approach for ground response analysis, whether you want to carry out equivalent linear or purely nonlinear, that depends upon the type of facility. So let me explain you one-dimensional equivalent linear method. So mostly because this is widely used for several, infrastructure projects. So that's why I just take it up. Nonlinear models, as I said, like we do have different kinds. So two-dimensional and three-dimensional equivalent linear models, also SASI, which can take care of, of course, these are very costly. That is the problem. Only few companies, afford to buy this or use this. So SASI is a very, and we do have our own code for, which can almost do the similar things like SASI. So maybe if possible, I'll just go to that section where we have done the soil structure interaction for the pile rough structures. So to incorporate all this, finally, I have to understand the SSI effects, or I can more specifically DSSI analysis, like dynamic soil structure interaction effects, where I need to have the exact ground motion characteristics. Okay, and at the free field, that is at the surface, so that I can use that as an input when I'm designing my superstructure. So structures which respond differently if supported on soft soils, because it depends upon the overall interaction effects, because it behaves like a system. You have a soil, you have a substructure, you have a superstructure, and all three are having, different material properties, and it has a different fundamental frequency. Soil has a different fundamental frequency, earthquake has a different frequency, and my superstructure, if I consider the foundation, everything as a one unit, so that has a different, fundamental frequency. So when the three different things comes, I may end up with some resonant effects also. So all these things has to be, evaluated during my analysis when I'm doing the seismic designs. So the dynamic response of such structure itself would induce deformations, because it's a complete system. I need to understand what is the overall, displacements or the stresses in my superstructure at different nodes can be evaluated if I do the detailed dynamic soil structure interaction. So this process where, like, you will be finding out the response of every element, like, at different nodes we have to evaluate, so that we can understand its significance Okay, whether my particular facility is behaving fine or not. See, I'll tell you one more thing. Even with this, there is always a question like, can't we design earthquake resistant structures? So why can't we design, if a facility is designed for a magnitude 7 or like 7.5, so if you get a 7.7 earthquake, obviously your facility may not perform, right? Or like if the duration is, if the event is higher, like you designed it for a particular seismic event of some duration x, if the duration of the seismic event is something x plus delta x, then again your facility may damage. So because earthquake is such a complex I think it doesn't have only the earthquake magnitude. It has different parameters which has influence, including amplitude parameters like acceleration, etc. You have frequency parameters and also the time parameters or the duration parameters. So you cannot design for such a varied parameters. If you design it, obviously the cost of the particular thing goes up. And if you design such thing where you never had an earthquake before, okay, then there is complete waste of money. So rather than this, like base isolations or some kind of system, you have to shock absorbing systems has to be designed. That may be the better way when you really want to have a resilient infrastructure. Because this soil during this ground motion analysis, it there is like it behaves like a filter, like it is altering, right? Anything that alter the input ground motions, it's like a filter changing the characteristics. So because there may be change in the different parameters, like frequency content will change, and whatever the layer, the soil layers, that complicates the issue, because each and every layer we do have different ground motion characteristics. And because of this, the accelerations or the site amplification or even the de-amplification, if it happens, we are happy. But if there is an amplification, then of the input ground motion from bedrock to the surface. So in Delhi, when we did the analysis, we observed like the amplification ratio was even approaching 2.2 in eastern Delhi. That means at the bedrock you have acceleration of some x, and in at the surface in some regions of Noida it's going 2.2 times of x. So that means you cannot take x as your design characteristics for your seismic design. So you have to actually calculate the site specific amplification factor, and then use that parameter when you are doing the seismic design. And also duration, as I said, if you design a facility for some x duration, if x plus delta x comes, obviously it may fail. Okay, so let me tell you about the site amplification, because that's also one of the important quantification we do in ground response analysis. I have a bedrock acceleration like this. Okay, when I bring that to the surface, equivalent linear, whatever it is, this is my acceleration. So 1 over the above gives me the amplification, right? So B by A gives me the amplification factor. So because the soil is more loose, so it can amplify the seismic wave. If the input ground motion is x, it may be x because it is on the rock and it's mostly elastic, but it may be something around 2x, then obviously your facility with the same kind of design parameters will not work. So that's what happened here also. I'll just keep setting something. Okay, so how to do that amplification? As I said, amplification is nothing but, see, again, I'm just going to that figure where I can show you the bedrock ground motion, outcrop ground motion, and surface ground motion. So amplification will be whatever the ground motion here divided by bedrock. If it is here, outcrop by bedrock. But in mostly, since it is behaving like elastic, rock is elastic, so you may get amplification is equal to 1. So whatever here, it will be here only. Okay, but whatever here is not here, because the soil do alter, acts as a filter. So let me show you some examples. This is actually used with the Dectra. It was initially in Spanish, so that's why you see this is all in Spanish. So beta is nothing but shear wave velocity. This is gamma. This is the damping and the thickness of each layer. So you have to give some input ground motion. Let's assume that we have given the Booz earthquake ground motion, and so these are some of the properties, measured properties at Delhi. So in some part in Delhi, so no, I don't remember that. So shear wave velocity, which has been measured through MSW. Of course, damping we have assumed 5% because it's not easy, because damping in lateral direction is different than damping in vertical direction. So which we will be evaluating, with proper field test in the field, especially when we are doing some power plant sort of things. But whereas for normal structures, you can consider both horizontal and vertical damping as you say. It's not like structural damping. You can even have 20% also. Okay, so see here, this is somewhere in Vasant Kunj, which is in the South Delhi, which is sitting on the rock outcrop. So this is actually the A. Okay, so input ground motion, and this is at the B. Okay, mostly when we divided, B by A, so our spectra was like almost like a flat. So it is almost like a one. I'll show you the one which is at sector 51 Noida. This is at the input ground motion at the rock, and this is the surface ground motion at this surface of the soil. Okay, and 1 over the other, that is B by A, which gives me the amplification factor. So you can see here, this is something like almost 1.8 or something. Okay, so we have developed that. This is actually part of my PhD as well. So this is the amplification factor map which we developed for Delhi. So different locations, since we have considered 180 locations, we have done MSW, and we got a lot of site specific geotechnical data. So when we have done that in the South Delhi, okay, you have the amplification factors, not maximum 1.2, whereas Western Delhi it's between 1.2 and 1.8, whereas in the Eastern Delhi where you have like Yamuna Vihar, Pragati Nagar, Pragati Maidan, and Mayur Vihar, etc., Noida. So mostly the very costly areas these days. So it was like ranging from 1.8 to 2.4. Okay, so the maximum that we got it is in 2.4. So that means like if input ground motion is some x acceleration, it will be 2.4x maximum. So you cannot design the facility same as here or here or here. So it is hazard is very site specific. Generally, the piles in such kind of areas where you do have amplification, higher amplification or liquefaction hazards, what we do is like we generally go for deep foundations, and the piles are very common. And these days, people we are coming up with the pile raft, because Terminal 3 of Delhi Airport is on pile raft, whereas Terminal 1 is on pile foundation. So there is a huge amount of money, and it's been saved because of adoption of the pile raft foundation system in Terminal 3. I don't go in detail for that, but anyway, so piles generally they can take care the forces because of this kind of movement, or like whatever the inertial forces which can take care of the amplification and the liquefaction issues. So what exactly we do consider when we design a facility? We have that seismic forces, and then inertial forces, and of course because of the any geotechnical hazard, we do have soil failures also, like liquefaction, etc. So to address this, after you do this detailed ground response analysis, we have to adopt this soil structure interaction. It's a very, people think that it's like a myth in the industry that it's a very what to call the robust or like complex approach, or it is costly, it makes the design costlier, etc., etc. But these are also myth, because it can even reduce the cost. What we are trying to do here is we are trying to quantify the exact hazard. Okay, when you quantify the exact hazard, the cost, it may be underestimate or it may overestimate, whatever it is. So it will give you the exact evaluation, so that will be more safer for my design. So because this involves the relationship between the soil and the superstructure or the substructure, I can say that complete structure. So how they do behave, because these two are different materials, and effect of these ground motions, the structural experience because of the seismic events can be quantified, and of course it depends upon the vibration period and characteristics of the soil. These are some of the questions which we generally encounter. How does the interaction between the soil, foundation, superstructure affect the dynamic response of the overall structure? Yes, because the wave is passing through the below the ground from rock to the soil. We do get altered, which I discussed extensively, and this is like ground response analysis. When this modified wave is coming and hitting the pile foundation or whatever the foundation that we have it, there is a different inertial forces are getting induced, and that we have to do it not just from some value of PGA at bedrock, which may be much lesser than actual PGA. So obviously the system failed. So, and will the foundation safely transmit the inertial loads into the ground without structure experiencing any excess? So this, we have to calculate the seismic settlement analysis has to be done. I just putting some questions which I generally get it from the industry. Will the inertial loads or the wave induced that ground displacements, which are subject the piles to larger bending moments and shear deformations. Okay, so for that only we have to do the site-specific analysis. So will the axial capacity of the pile be affected by stresses or soil degradation that's caused by the earthquake or the soil degradation? Okay, that can be done by through proper ground response analysis. So with these questions, let's see what the code says, right? We do have seismic code of course, that's like a more generic one with a guidelines only. So the code not always includes analysis since SSI usually reduces the accelerations and stresses in the structure. It's important from strong motions, especially when you are designing some facility in seismic zone 4 and above. And the current seismic codes use the reduction factor, which help to define the design-based shear from elastic response spectrum. And the current building provisions use a fundamental vibration period, which is a vibration period into the period lengthening ratio R, and which is depends on the lateral stiffness of the structure, stiffness of the foundation, and the soil, and of course its height. These are our status now. So, which are the factors that dominate the nonlinear dynamic soil response, like hysteresis behavior, as I shown you that stress strain curve, and stiffness degradations, non-proportional damping, as I said, like lateral damping is not equal to vertical damping, there's highly non-proportional damping, and of course the massing phenomena. These are the four factors which generally dominate the nonlinear dynamic soil response. So to carry out or to consider that, we do SSI analysis. For doing that SSI analysis, we do have different techniques. Okay, the literature, continuum or discrete models, direct approach or substructure approach, which people mostly do this approach, two-dimensional or three-dimensional based upon the type of problem or the facility you're going to do, time domain versus frequency domain, and linear versus non-linear solutions. So I'll just explain you each technique quickly so that I can complete the ground response analysis. Actually, this is a one chapter, like in the course at Geotechnical Engineering, which I'm trying to cover it in 1.5 hours. So continuum versus discrete, it basically lies with how you are doing the numerical formulations, and mostly similar results you get, but the difference comes when the spatial interpolation or the size of the mesh we consider, or time stepping. So the discrete mostly heterogeneous on laterally and vertically. So we can use BM, or people also going for DM these days. Direct approach and substructure approach. I generally do this one. Okay, we do go for the direct approach. So in direct approach, what we do is like we model everything together. Okay, so either two-dimensional or three-dimensional soil, substructure, superstructure, everything we consider as same, and we do that. In substructure approach, so first people do the soil part embedded with the substructure. Whatever the response comes, that they go it as with the superstructure part. Two and three dimensionals, it depends upon the type of problem, whether if it is a retaining wall, then you two-dimensional analysis is fine. So it depends upon what kind of facility you are going to work on. Time domain, frequency domain. So maybe it depends upon whether you are doing with the Fourier domain due to frequency dependency, or of the whatever the foundation stiffness, or if the problem involving nonlinear material behavior, or normally we solve it in time domain. So linear nonlinear solutions. Most analysis, in general, what we do about linear and vibrations of the soil properties to the level, because it's more simpler when I say with the non-linear part. If you take the soil constitutive models and the non-linear soil models, then we can incorporate that. But for that, you need a lot of information about the dynamic soil property behavior. As I said, you have to do dynamic soil tests like resonant column in the lab, or any field test, dynamic test, so that you can get the complete nonlinear soil properties. So then you can incorporate that. So what are we assuming? Like in all these analyses, the basic thing that we assume is like the seismic wave is propagating vertically above, but it can come in any direction, right? Not much. Excuse me. Not much research has been done in that aspect, and
Ma'am, sorry, ma'am, but the slides are not changing, ma'am. It's got stuck, ma'am.
where it was stuck.
Ma'am, calculating top of profile motions.
No, no. Madam, It's changing.
Okay.
Ma'am, please continue. There may
I'm
be
with
some
the
issue in
classification
madam
of
system.
exercise techniques now. Is it fine?
Yes, ma'am. We are able to see.
Okay, direct approach, two and three-dimensional frequency domain. This I explained, linear, non-linear explained. Now I'm here, I guess.
Yes, ma'am.
Okay, shall I proceed?
Yes, ma'am.
Okay. So these are the assumptions which we do in SSI analysis or DSSI analysis. We consider that the seismic wave is hitting vertically above, but it can come in any direction, right? With any angle of incidence. So, okay, it's not coming vertically and hitting your foundation, right? So that is a basic thing. Some very little literature has been done. If anybody is interested, I think this is one good problem to solve. And we consider soil is layered. I'll show you some of the two-dimensional soil profiles in Delhi, which we prepared. Soil is not like a layered like we assume. Okay, it's highly heterogeneous. In between, you have a kind of capsule kind of clay formation, or you have a big boulder. So soil is it's not completely like a layered. So we do this assumption because of our simplicity in calculations, and linearized non-linear soil models. We generally assume that. So yeah, this is how the soil profiles for Delhi in some regions. You can see here, this is in some eastern part in Delhi sector 1 to 61. So where is it layered? It's not layered, right? It's like highly heterogeneous. So then coming to the sources of uncertainty. So the first one is with respect to the nonlinear soil behavior. So you have to do a lot of dynamic soil properties test, and then build structural properties. The structural material have it's a continuous material, right? I don't see much variation with the material properties. It's just a concrete or the steel, right? So and what is that big thing that it has? It like in terms of properties or variation. So the dimensions and the elastic properties are not exactly known at the design stage, but model used to reproduce the structure in you doing the SSI analysis. And numerical solution, computational algorithms are not always clearly described, especially when you use any kind of software. So I can say that my first PhD student, she worked on dynamic soil structure interaction of a pile draft foundation for a symmetrical building. If Amit allow me, then I can talk on that aspect, because that particular research problem has considered most of the things which we discussed here in today's class. So
Yes, ma'am.
is it an expensive analysis? I'll talk on that tomorrow then. Okay, so that it will
Okay,
be
ma'am. No problem.
what I discussed today.
Yeah.
So last question many people in the industry ask, is it like very expensive analysis to do it? So I say that it is not expensive, but it's very important, rather than it's like in your health insurance, right? What we do is like we do insurance for everything, but not to our structures, etc. So it's like health insurance. Uh, So we need to characterize the soil basically for its dynamic soil properties, and then we can use that nonlinear soil property analysis or ground response analysis. So this is how I'm just giving you some guidelines, I can say, to do this. Okay, so from the codal provisions as well, taking the story ratio and shear wave elastic characteristics, etc. So considering that, you can calculate whether it is required or not for a given location for the given facility. Okay, in terms of the structural properties, its material characteristics, and the dynamic soil properties. And just see this. This is a chart to show you that SSI analysis for steel and concrete chimneys, because these are all like tall ones. So for based on the slenderness ratio, so shear wave velocity, the steel chimneys and the concrete chimneys, so they are higher for the concrete. This it shows the only the limiting shear wave velocity, below which if it is less than that, okay, the slenderness ratio, just go there and you get some shear velocity from the chart, and from the site, if it is less than this value, okay, so maybe interaction could be more significant, so you have to do the SSI analysis. So these are some of the broad cross checks whether you have to do detailed dynamic soil structure interaction for analysis for particular facility when you are going to design it or not. Similarly, for concrete structures, if the shear wave velocity at the site is less than this, Okay, so based on that, you can select whether you must do it or not. So these are some of the guidelines only. So there are something about the soil models. Okay, so different soil models, and of course, it's coupling to the superstructure. So we do have various, soil models for comprehensive dynamic soil structure and traction analysis. So one is like equivalent soil springs, so which we consider to be connected with the foundations, and we model it as a beam, element, or plate or shell. FEM, either two-dimensional models. Mixed FEM and BEM approaches people have done in the recent past, which is very popular. And for all these options, whatever the spring elements, they're connected to the superstructure, they still remain the most popular model, especially when you are designing, because it's very simple. Time doesn't take much time, so it's easy to model. That's the reason why people do. And also, in exceptional or very important cases, this FEM or BEM, we can put it in use, and it is of course mostly restricted for two-dimensional analysis, not for three-dimensional, as it makes the problem more complicated. So the step one is like, you have to do the soil response analysis, realistic estimation of the seismic environment, vertical inclined surface waves, and then depends upon the geotechnical and seismological data that is being for that particular site. So as I said, like, we consider the wave is sitting vertically up, right? It may not be, it can hit 30, 40, whatever direction. So anyway, that's our assumption. And for soil, the structure part, soil pile structure system, so we can consider either direct approach or substructure approach. In this one, you first calculate the free field, then put your structure. Okay, otherwise you can completely model it as a complete system. Okay, and then the second step, you have to evaluate the pile response, kinematic pile response. So response of the foundation, ignoring the inertial forces from the structure. So I don't consider anything superstructure, so only embedded foundation system. Then we'll determine the oscillatory motion at the raft. So this is for the pile raft, which I'll discuss more with our research part. So in this one, raft is a mostly load-bearing element, and pile will be a settlement reducer. So that is the most advantage of this pile raft system. And the bending moment, shear forces of the piles because of the seismic waves can be evaluated. And then the third step, I can put the initial loads that are coming from the superstructure, and then dynamic motion of the structure and the loads. So finally, we can determine the whatever the dynamic forces, settlements, and at different flows at different nodes, we can calculate that so that we can understand the overall response of the superstructure. So to do all these things, first thing is like, of course, principles of meshing. So there are standard methods. I'm not going in detail with how to do meshing and all, because this may not be exactly related to ground response analysis. So just as a word from the geotechnical perspective, irrespective of whether we use springs or FEM to model the soil, the fundamental property on which the stiffness depends are like dynamic soil properties, that is shear wave velocity, shear modulus, and the Poisson's ratio and the dynamic damping ratio. So these are very important to quantify by doing either lab or field test. And then, in spite of all these things, so maybe still we do have some uncertainties to be handled. So that can come with your judgment. So there is a lot of judgment involved in geotechnical engineering. So in addition, it's like a more of common sense rather than, you are only mechanics. So it is also preferable to do parametric study by varying design different soil properties. So I'll explain this tomorrow more. You can understand more. So with this, I just conclude it's much better to do little more analysis before rather than to be sorry at the end, because once the soil fails, structure must fail, because no structure can, if anyone say that fly, float, or okay. Thank you so much.
Thank you very much, ma'am. Please ask your questions if you have any
If you have
query.
any questions, let me know.
Madam, I have one question.
Yeah, please.
Ma'am, as the ground motion depends upon the behavior of soil, particular type of soil. Similarly, is there possibility that time history also depends upon the type of structure on which we are applying, or
Yeah,
how we can select a particular time history for
yeah. See, the thing is here is like, modeling or doing the analysis for the superstructure is
now?
much easier because, am I audible, Amit?
Yes, ma'am.
So here the thing is the more complex part is with the behavior of soil, especially under dynamic environment because it is highly nonlinear. So if you can quantify that, that can go as an input. But the remaining part with the superstructure is much easier. The material is not that complex because it is uniform. It is not particulate.
So means, madam, we can use any type of time history on any type of structure.
No, it's not like any type of synastry. If you can evaluate properly the ground response analysis up to the free at this the surface level, okay, that you can use it. So the main
Madam, you are not audible, ma'am.
I'm not audible.
Now you are audible, ma'am.
Acha. Okay. So what I'm saying is the main crux, what we observed in the past, based upon the past, classic events was bringing the time history from bedrock to the surface. Okay, which we discuss now with the ground response analysis is the most crucial in the entire dynamic analysis or like earthquake resistant analysis part. So why? Because once you can bring it to that, then it is that can go as an input for your superstructure. The major flaw with our especially the Bhuj earthquake was people were designing considering the acceleration at the bedrock only, that is time history at the bedrock only. They could not consider the surface time histories because the ground response analysis up to 2001 Bhuj earthquake, geotechnical earthquake engineering was like people were not, because this is a very new discipline, so people were not even aware of what is liquefaction and what is ground response analysis. So I can say that this is actually eye opener for most of our research that what we have done, especially in the last 20 years, I can say.
Madam, one more question is there.
See, I cannot say for this, but I can see somebody from Renuka Nagpal, right? So what should be K value for black cotton soil for FEM? See, for dynamic part, you have to do detailed, test, as I explained, either field test or laboratory test. There are some range of values given even in some of the codes, but you have to site specifically, you have to evaluate that. Renuka ji, is that fine? Okay.
Yes, ma'am. Ma'am, is there any site from where, like USGS, where we can download Indian time histories so that we can directly apply
Cosmos,
to our structures?
yeah, the Cosmos website you can download, right? The
Yes.
IT Roorkee is maintaining. I'm not sure. Recently, I didn't open that, but I think you can ask Swati. Swati can help you in that. I gave you
Okay.
a right. So I think tomorrow. When is the talk? Swati का कब है?
मैम 11:30 आफ्टर यू आपके बाद में मैम.
अच्छा ठीक है, no problem.
Yes. Um, all the participants are requested to write or mail us the questions if they have in their mind after the lecture also, so we can.
We'll leave my email ID so in the
Okay,
chat
ma'am.
box. So thank you so much for this opportunity and to interact with all of you. I'm dropping my email ID. Anybody who is interested to have some collaboration, so please mail me. And especially UG students, we do have internship program which is online now because of the pandemic. So can also contact this email if they are interested. If they are really motivated, then please contact. And we do have a QIP program for PhD. If any young faculty wants to do PhD, so we do have QIP program. If not, there's a sponsored category wherein like your organization can sponsor you. Okay, so then you can do PhD also. So that's all. Thank you so much. Thank you to organizers, especially to Dr. Amit. Thank you.
Thank you very much, ma'am.
Thank you, ma'am.
Thank you.
So please write to us if you have any query and directly mail to madam also.
So that was Dr. Nilima Satyam ma'am from IIT Indore. She enlightened us regarding the earthquake aspect and how to measure the different aspect areas. So the next session will be at 2 p.m. by Dr. Golubev. He is a faculty at Russia. So Moscow Institute of Physics and Technology, Russia. So we hope to see him at 2 p.m. Uh, so that's for this session. We'll be meeting after the lunch break. Thank you so much.